So yesterday we were learning about A-star algorithm, and we learned that A-star algorithm is a class of algorithm which is called a graph traversal algorithm. So it's in the same family as things like depth first search, breadth first search, and Dijkstra's shortest path algorithm. A-star has like a little extra characteristic on top of, say, Dijkstra's shortest path algorithm, in that it uses a heuristic to decide which nodes to expand in the navigation graph at each iteration of it, right? This is basically the pseudocode, and I probably should have started with this yesterday. This is the pseudocode for A-star algorithm here. If you want to look at this pseudocode, there's a paper that's linked to from the course website, and it's a paper that I published at a conference called C Games in Louisville in Kentucky in 2016, back when I started teaching game programming, first of all. Game engines, and 2006, and this algorithm talks about an implementation of A-star in C++ that I wrote for as part of the course, right? So here's the pseudocode for the algorithm anyway. The pseudocode for the A-star algorithm looks like this. So you pass in the start node and the end node on the graph that you want to try and find the shortest path between. And this algorithm keeps track of nodes on two lists called the open list and the closed list. So the first thing that happens is the start node has an FG and H score of 0 assigned, and then this gets added to the open list. So basically the start node is the only node on the open list when the algorithm begins. So then this algorithm proceeds in a while loop so long as there are nodes on the open list. These are nodes like still left to be expanded. And the next thing that happens is the node with the lowest F score gets popped off the open list. And then the algorithm checks to see if that node is the destination node. And if it's the destination node, then that means the algorithm has managed to find a path, and the algorithm then iterates back from the destination back to the start via all of the parent nodes. That's how the path is actually constructed. So if the algorithm hasn't found the end node, then the node that gets popped off the open list now gets pushed onto the closed list. And then all of the nodes that are adjacent to the node that we just popped off the open list, they get expanded and they get added to the open list. So this is how this particular part of the algorithm works. So for every adjacent node, and this is basically a node that is connected via an edge to the node that we just popped off the open list. So the first thing that happens is you check to see if it's not on the closed list, and if it's not on the open list already. So this is basically a new node that the algorithm has encountered. So it's not on the open list. In other words, we haven't looked at it already, and it's not already on the closed list or the open list. The F, G, and H scores are calculated for that node, and it gets added to the open list. So I'll just like what are these F, G, and H scores? The H score is the heuristic cost to the end, and yesterday we looked at like there's probably more, but there's at least 3 heuristics that could be used. Heuristic number 1 is just the Euclidean distance, so the straight line distance between the node we've just popped off and the destination. So that's just going to be like the square root of the x's to be squared plus the y's to be squared plus the z's to be squared. In other words, the distance between the node that we've just the node that we're going to expand, the node that we're just about to add, and the destination. So that's the H score. The G score is the cost to get from the start to my parent plus my parent to me. So that's the G score, and then the F score is equals to the G score plus the H score. And then so that node gets pushed onto the open list. Otherwise, like you can see, the algorithm here has an if statement here. So the algorithm is checking to see if it exists on the open list. If it doesn't exist on the open list, it gets added to the open list. If it already exists on the open list, then that means we may have found that this via a different path through the graph. And then the algorithm implements this thing called edge relaxation. So edge relaxation means the node is already on the open list, but now we found it via a different path, so possibly this path is going to give us a lower cost. So we recalculate the F, G, and H scores, and then we check to see if if the G score, in other words, if the cost of getting to this node via this path is lower than the cost, previously, then we're going to update the node's parent to say like we found a new path, and then we update the node's G score. So the node basically just gets updated with a new parent. So that is the pseudocode for the A* algorithm. Alright, so like again, basically it's got open and closed list. You pop the start onto the open list, pop the node off with the lowest F score, check to see if you've reached the destination. If you have reached the destination, iterate back from the destination back to the start via the parents. Otherwise, you expand all of the adjacent nodes and push those onto the open list. And this is the heuristic thing here, because we're always taking the node off with the lowest F score. So that means, like, unlike, for example, the breadth first search, which just expands outwards constantly, expanding nodes, expanding nodes, expanding nodes without being directed. This is a directed graph, so we're kind of trying to expand outwards from, or we're going to choose the node which is more than likely going to end up part of the path, and that's going to be the node with the lowest F score. And like I say here, once you pop a node off the open list, you calculate you basically go through all the adjacent nodes, calculating their F, G, and H scores, and then push those onto the open list. If it already exists on the open list, maybe we found this node via a shorter path, and so you update the node on the open list. And that is the A* algorithm. That's the pseudocode, everybody. Implementing A* in C#, you can basically take the pseudocode and map it onto C# code. So I'll show you what it looks like in this example here, which is called pathfinder.cs. So we'll see basically how this maps onto the pseudocode. So again, we keep open and closed lists here. I'll talk about how we access nodes on the open and closed list in order to make the algorithm very efficient in a little bit. But basically, this algorithm this C# implementation has an open list and a closed list. So here's this method here called find path, and this method, first of all, is rounding the position, the start and end position, to the nearest, like I call them, they're voxels, but they're basically the size of the navigation graph. If we want to basically, this is going to generate this doesn't use the same algorithm as Unity. Unity uses an algorithm called triangulation, but what this is doing is basically placing a node every interval, and this interval is determined by, I feel like, the voxel size. What did I call it here? I call it the grid size. So basically this is saying there's going to be a node, let's say every 5 units or whatever, it's going to have a node, and all the nodes can be traveled through or traversed via their adjacent nodes. I wonder, should I draw some diagrams for this? Anyway, here we go. Here's the while loop. So I'm basically saying while open.count is greater than 0. In other words, while there are nodes on the open list, what happens? We pop off the node with the lowest F score, and this is a priority queue, which I'll talk about in a little bit, but this is popping the node off with the lowest F score, checking to see if the node is equals to the destination node, and if it's equal to the destination node, found is equals to true. We break out of this, iterate back from the destination to the start via the parents, and make the path like that. Otherwise, there's this method here called add adjacent nodes. So add adjacent nodes in this example is using a 3 nested for loop. So this is basically saying, or maybe I should draw a diagram for this. This is basically saying that, because we have a square grid, we have like a grid where every node can be traveled to via the adjacent nodes around it. You can write like a three sort of level deep nested for loop for this, So just going the forward nodes, the 3 forward ones, the 3 behind ones, the 2 to the side. Well, of course, there's more in 3D because you got 9 above, you got 9 nodes below, you got 3 in front. So that's 9 and 9 are 18 plus 6 is 24, 25, 26. I think there's in total 26 adjacent nodes for every node, and that's what's happening here. Add if valid, then it's going to check, first of all, I do a ray trace to see, is there a node there? Is there something that I can travel to there? Here's checking to see if it's not on the open list, if it's not on the closed list. We're creating the node and adding it to the open list. Otherwise, this algorithm does this edge relaxation thing where we update the FG and H scores and say we found a new parent. So that's the essence of the A-star algorithm implemented like in a very kind of like, I suppose, simple enough C# implementation. There's also a method here called smooth path, which is quite nice. Because my path is essentially like a grid, we're going to end up with lots of unnecessary waypoints in the graph. And what smooth path does is it just basically says, okay, to get from this node to this node, can I get from this node to this node without bumping into anything? Or can I get like between sort of one node to maybe a node ahead? Can I basically delete elements from the path and still have a smooth path? That's essentially what's happening here in the smooth path thing. So let's see what it looks like. And here's the heuristic doing the, this is Manhattan distance heuristic. And then if this cost function is either going to be 10 or 14. 10 to travel vertically or horizontally, and then 14 to go diagonally. So that's the A-star implementation. Let's jump over here into Unity and see what it looks like. Here's what it looks like in Unity, implementing A-star algorithm. So there is a little void down here at the bottom. And this void wants to get as far as the destination node, or the destination, which is all the way up here. And these spheres here are tagged with the obstacle layer. So you can select the spheres and drag them around, and you see it will recalculate the path basically to avoid the spheres. So there's a few parameters that we can set on this algorithm here, which are interesting to note, right? First of all, here's basically the Pathfinder algorithm here, right? So it's saying it takes less than a millisecond basically to calculate this really small path. The grid size is, you know, like I say, where is it going to place nodes on the navigation graph? So if you set the grid size to be really big, then you can see, like, you know, the graph essentially is, you know, every 20 units, it's now going to create a node, as opposed to like every 10 units or whatever. Like you can make that 1, and you get like this really, you know, path with loads and loads of nodes in it, because basically it's placing a node, you know, every 1 unit. And it's doing a raycast, like it's doing a raycast from a node, like for all the adjacent nodes, and that's why it knows not to place nodes inside here. And you can see it can move this. Now you can see actually the Pathfinder, because there's loads more nodes on it, it's taken 82 milliseconds now, okay? So, what else can we say here? If I make the grid size 1, a couple of other things you can do here. You can say whether you want to have 3D paths. Oh, okay. What's the story here? I think it's because we've got loads of nodes now. Maybe doing the 3D things is just taking too long. Let me make the grid size back to be 5. And let me see if I can do 3D. So 3D basically says, do I want to create nodes above and below the XZ plane, or do I just want them created on the XZ plane? So I think if I select one of these obstacles here, like this guy, bring it up here, hopefully it should create nodes on the XZ plane, and also nodes that go up and down as well. I don't know why this isn't working. Let's see. This was working yesterday. Pathfinder is 3D, so it should be creating nodes above and below as well. What? That should be creating nodes. Oh, there you go. So you can see now when we zoom in here, it's also created nodes, you know, to travel downwards instead of just on the XZ plane as well. Because I'm also adding, like, you know, the 9 above, the 9 below, plus the ones in front, plus the ones behind, plus the 2 to the sides as well. So that's that thing. And then I could just show you can smooth the path then as well. So if you smooth the path, okay, it's taking a little bit longer now to execute. You can see when you smooth the path, it removes lots of unnecessary waypoints from this voxel-based graph, so you get a much smoother path like that. So that is what A-star implementation might look like in C#. Now, there was a very important learning outcome from this like little study, and that's how do you store the open and closed list in order to make accessing elements on those lists really fast. And let me get my whiteboard up here and we'll just have a little discussion about this, right? Because this is kind of an interesting little discussion. So, yeah. Here we go, here we go, here we go, here we go. Okay, so what do we want? Guys, computer science people, I guess you hopefully know this. You've heard of this thing called big O notation. Big O notation describes like the efficiency of an algorithm and how this algorithm scales when the number of elements that the algorithm has to iterate over increases basically. So this is called big O notation, right? And like we got two data structures. We got the open list and we also have the closed list, right? So like maybe if you guys can have a think about this and I'll keep talking. You know, why would you choose, like, for example, an array over a hash map or some other data structure? Like, why would you choose, you know, what criteria would you use to determine, like, what you would use to store, you know, elements on the open list and closed list? Like, why would you choose, for example, a list over an array? Let's see our candidates for open and closed list. We could potentially store them in a list. We could store them in an array. We could store them in a hash map. MAP. And let me see if I want to maybe just want to draw a table here. Array. Just put these three down for now. You can't add items to an array. Fantastic. Okay, so an array is kind of out the door straight away because an array is of fixed size, and we want our open lists and closed lists to grow and shrink. So maybe a list or a map might be a better candidate. What else would you decide? Like, why else would you, for example, why would you use a map over a list? By a map, I mean a dictionary. I think a map is actually called a dictionary in C#. In Java, a map is called a hash map. But these are basically like they are like index data structures. Like, why would you choose to use a map over a list? You know, they can both store multiple elements. They can both grow and shrink. Why would you choose a map over a list? Any thoughts, you guys? Like, why would you choose one data structure over another? By the way, these are very typical questions that you get in Google and Facebook interviews. You know, the difference between a map and a list and why you'd use one over another. And here's like a classic example of, you know, we need a data structure with certain performance characteristics. So we're going to choose like particular data structures to implement this open and closed list thing. Why would you choose one over another? A map allows for instance the keys. Yeah, cool. A map doesn't contain objects in particular order. Okay, cool. So lists are sorted, or they're in a particular order. Dictionaries and maps are not sorted, or they're not in any order. An array obviously is in a particular order. Well, I'll tell you, the reason is, like, it depends on how you want to look up things, okay? So, for example, if you want to, like, let's put a couple of options here, right? If you want to, I'll just put a couple of thoughts here, okay, about, you know, different ways we want to access this. And we can put the efficiency of these data structures in here. I don't know, maybe I don't need all these columns, but we'll see. First of all, what about, we'll say, adding an element to the end. Let's say retrieving by value. Now, do we want to say retrieving by value? Retrieving by index is okay. Retrieve by, let's say retrieve by a key. Let's also say deleting in the middle. Like, actually, you know what, this discussion could go on for a while. Let's just like put a few thoughts in here, okay? So first of all, adding to the end of the list, that is going to be an efficiency of ON. No, hang on, adding to the end of a list, of course, is an efficiency of, I don't know why this undo takes so long here. Adding an efficiency here is, of course, O1. All right, so you add something to the end here, it's an efficiency of O1. Adding something to a dictionary or a map, what's the efficiency of that? Inserting something is actually O log n, isn't it? I think it's O log n for a map. For an array, again, it's going to be O1. Retrieving a specific element, right? This is retrieving by key. This is like retrieving a specific one. If I want to pick an element out of the list here, okay, if I know the index of it, then it's just going to be O1. But if you don't know, then you got to search the list. You got to search the list for it. So this is going to have an efficiency of ON. Because maybe you got to check the list for every element in the list to see does the element exist on the list. And if it exists on the list, then you return it. But you have to potentially search every element on the list. For a dictionary, the efficiency of retrieving by a key is always O log n. So O log n efficiency is really, really good, because O log n efficiency is this sort of graph here. It means that if you have, like, we'll say 5 elements on a dictionary, you know, the efficiency is going to be this. If you have 5 million elements on the efficiency, 5 million elements in a hash map, then it doesn't really take any longer to retrieve. If you have like 5 million elements or even 1 billion elements from a hash map, it doesn't really take any longer to retrieve it than it does if there was only 5 elements on a hash map, because they're key value pairs, right? And it does an index lookup. The array, again, if you want to retrieve in here, it's going to be ON. So, looking at the open list and the closed list, what do we need to do? We need to check to see if something is on the open list or on the closed list. So that's this retrieve by key thing here. We need to search the open list and the closed list for a match. So using a list is okay, but it just means potentially, like, if I have, we'll say 10,000 elements on the open list, and maybe I have to write for I equals 0, I is less than 10,000. So I have to iterate through every element on the list in order to see does something exist on it. Much better data structure then is a dictionary, because this is O log n. It means no matter how big the open list or closed list gets, we can always retrieve with like a similar level of performance. So O log n, a dictionary, is fine for checking to see does something exist on the open list or the closed list. The other way that we need to access the open list and the closed list is we need to retrieve the node with the lowest F score. So that means potentially like searching through, you know, this dictionary, and we got to search through every element on it to see like which is the one with the lowest. And we might write a for loop to go through every element on the dictionary, and then we'll have the minimum value, and then we'll write for I equals, you know, if it's less than the minimum, becomes the new minimum. So if we use a dictionary, so this is basically retrieval with lowest score. And if we do retrieval with lowest score with a dictionary, then it's an ON search. However, you guys might know, you might have come across another data structure, which is actually the perfect solution to this one, and it's called a priority queue. P-R-I-R-I-T-Y. It's called a priority queue. So a priority queue is a really cool data structure. A priority queue is a sorted queue. And when you insert something into a priority queue, it's got an efficiency of O log n. And I think when you retrieve something off the top of a priority queue, it's just an efficiency of O1. So for this thing, for retrieving things from the open list via the lowest F score, a priority queue is a good data structure. And this again is a very computer sciencey thing, where we actually are storing our references to the nodes on the graph in 2 places. We're storing it in a hash map, and we're storing it in a priority queue. We're storing it in the hash map so we can check to see does something exist on the open list, and we're storing it in a priority queue so we can always retrieve the node with the lowest F score without having to iterate through every element and find the one with the lowest F score. That is like a very important learning outcome for you guys. So the conclusion for this is implementing the open list. You store it in 2 places, in a hash map / dictionary, whatever you want to call it, and also in a priority queue. When you're adding nodes to the open list, you add them to both data structures. When you're retrieving nodes, you can search the open list for the one with the lowest F score by using a priority queue. You can retrieve a node, you know, to see does it exist by using the hash map. And then the closed list, because we just need to check, do things exist on the closed list? So that is fine, because we can just use a hash map for that. So from that little discussion, I want to like jump back into the code here and just show you how all this might work in practice. We'll look at the code first of all, and then I'll show you what effect like using the priority queue has on the performance of this algorithm. So here's the coding. Here's the Pathfinder code again. So you can see for the Pathfinder code, the open, I keep two data structures. The open dictionary, which is basically mapping from the position where the node is onto the node. And then a priority queue, which is a data structure that just keeps all of the nodes. And then these are going to be sorted in order of their lowest F score. How you sort this priority queue, by the way, priority queues are not built into C#. So this is one on a Google priority queue in C#. I found an implementation online. And here's the implementation of priority queue. So that's the implementation from that article there. It internally keeps things in a list. And then it has a method called enqueue, which is add something to the priority queue. And then this is dequeue, which means remove something from the end of a priority queue. And you can peek and you can count and you can toString as well. So that's the priority queue implementation. And here's the Pathfinder thing. So there's two options, right? Actually, I implemented both, so we can see the performance difference between using a priority queue versus having to iterate through every element in a dictionary. So here we go. Here's like the find path method. Here we go. So if it says if the use priority queue boolean is set to be true, the current is just to be dequeue from the priority queue, and it will retrieve the one with the lowest F score. By the way, it sorts things on the priority queue by using a interface on the node class. So you implement the iComparable interface on the node class, and this is what the priority queue uses to sort the priority queue. So here we go, you implement this interface and it's got a method on it called compare to, and it compares the current node to a node which gets passed in as a parameter, and then you return -1, 0, or 1 depending on whether the F scores are less than or greater than or equals, less than or equals to or greater than. So that's how priority queue works. And then here's Pathfinder. So yeah, when we're getting the node with the lowest F score, we can either get it from the priority queue, or this is, the alternative way, which is to iterate through every element on a dictionary, figure out which is the one with the lowest F score. This will work fine as well, it's just not as fast. And then when we're adding nodes, we add it to the dictionary, and we also enqueue it onto the priority queue. So I'm just going to show you what the performance difference is when you use these things together. So let's see, here we go. Here we go. All right. So just to show you, like you can basically say, use a priority queue or not use a priority queue. So if I hit the play button, let's see. I don't even think I need to hit the play button. I think it will just do the pathfinding code, right? Here's the pathfinding code. I'm undoing the smooth paths, right? Why is it not redrawing? So there we go. There's my path. Look at that. A star took 1 millisecond, and we're using the priority queue. Look what happens if I don't use the priority queue. It takes 3 milliseconds. So it takes 3 times as long to calculate the lowest cost path without using a priority queue as opposed to using a priority queue. And just to show you as well, if you change this grid size down to 1, like the time taken to calculate the A star is going to really jump up. In fact, look at this. Oh, the A star timed out after 5 seconds. So the A star isn't even out, like it's taking a long time. If I set my grid size to be, let's see, 2. Okay, it's taking 35 milliseconds. Because that means for every iteration, every time it pops, in order to find out which node to pop off the open list, it's got to iterate through all the nodes on the open list. If you use a priority queue, the priority queue is already sorted. So again, using priority queue, not using a priority queue, it's 35 milliseconds. Using a priority queue goes down to like, 15 milliseconds. So it takes like half as long. So that is how A star works. What I had hoped to do with you guys is I'll maybe very briefly show you this, because A star of course is built into Unity as well. There's why would you ever want to implement your own A star? Well, I can think of 2 good reasons why you would ever want to implement your own A star. Maybe 3 now that I think about it. Reason number 1, if you're using entity component system and you have entities and you don't have game objects with colliders and stuff on them, then you have to implement your own pathfinding, because the nav mesh works in the game object world and it won't work in the entity world. That's reason number 1. Reason number 2 why you might want to implement your own A star would be if you were implementing your own locomotion. So I'll show you this. If you're using the built-in nav mesh in Unity, like it has a thing called a nav mesh agent, and so that basically the locomotion system is built into the navigation system in Unity. But if you want to use voids or you want to use your own locomotion system, then maybe you have to implement your own A-star algorithm as well. The third reason, of course, is maybe you're not programming in Unity. Maybe you're writing it in processing, or maybe you're writing in C++, and you're not using a game engine. So you want to implement some pathfinding. It's useful to know how the A-star algorithm works. So anyway, and of course this being a computer sciencey thing as well, like we want to know, how these algorithms essentially work, and not just know like which buttons we need to click in Unity to make things happen. So anyway, just to show you, maybe to finish this thing here, there's my path. Let me make this thing of size 5. So I get this nice path, and why don't we smooth the path as well? So you should smooth the path. There's the path smooth. If I make the grid size a little bit bigger, maybe if I make it 10, I'll get a slightly nicer looking path. Whoa, that's taking ages. That's taking like 2 seconds to calculate the path. And maybe to do the path smoothing as well. 1 millisecond now it's taking. Anyway, I think I can select the void, and the void is enabled on the path. I think this is going to work. I was just tinkering with this code this morning, but you should be able to hit the play button. And there's the void now, following the lowest cost path. I don't know why that doesn't work. Sometimes Unity does that. When you click those buttons, it doesn't actually flip. Anyway, there it is. It's avoided the first obstacle. I should have some epic music on here. Da, 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 da. It has managed to find the lowest cost path there between the start node, the destination node, and there it is, finding its way towards the target. Why does that not work? Weird. Okay, there it is, finding the target. It's a pity. It's kind of nice to look at in the... Why does that not work? Let me flip it around here. That's so weird. Does that ever happen to you guys? That's been happening to me a lot. When I click on these little things here, nothing happens in Unity. Maybe it's because this thing is selected. Oh, okay, there we go. That's maybe why. Cool. Alrighty. Let's try again. So now we can see this little void autonomous agent. It just found its path. Happily swimming from node to node. There we go. Yeah, because this guy's got the harmonic behavior on it, it tends to stay on the XZ plane, so maybe sometimes it's not going to be able to go up and down. It's just going on the XZ plane. So that's why. Okay, there we go. So there it is. So I'm just going to leave this here for now. I'm going to finish with this one. I'm going to open one more scene, and in fact maybe I'm going to switch to a branch here, because I was going to talk you through this thing, but we're actually running out of time, so maybe I'm just going to switch to a branch here. Git checkout nav mesh. Okay, so I'm the nav mesh branch. Just to show you that there's one additional scene in the repo, so I'm going to choose open scene, go into the scenes here, and look at the nav mesh scene. So this is just a scene that uses the nav mesh in Unity. What I might do is share a couple of videos, tutorial videos, but just to show you, this is built-in pathfinding in Unity. So like previously we're looking at C#, but Unity has its own thing called the nav mesh surface. To get all of this stuff, you kind of have to do a clone a repo. Let me see. You clone a repo, you download some things, and then you get these extra components in Unity. I'll put links on the Git repo. You get a nav mesh surface. Nav mesh surface basically says this is your level, and you can bake a navigation graph. And when you bake the navigation graph, hopefully it's going to show me, where's my nav mesh? There's the actual nav mesh. So as opposed to using placing nodes, at intervals, what this is using is, I mentioned this in my slides yesterday, it's using an algorithm called triangulation. So it expands the non-navigable areas and places nodes basically at all the expanded geometry for anything that's not navigable. With this nav mesh thingy here, you add a nav mesh surface. Here's my little level, so there's walls in the level, and then you basically add a thing called a nav mesh modifier, and you say that the walls are not walkable. Then we generate the nav mesh. It won't include those areas. Then on the player, you add a component called a nav mesh agent. And then I have a little script here on the player, which is very simply just going to do a raycast into the scene here, and then it sets the destination for the nav mesh agent. Again, I'll put some videos up, tutorial videos on this stuff, because if we had a bit more time, I'd have spent a bit more time on this. But anyway, just to show you how it might work, you hit the play button. This is built-in navigation graph in Unity, and then so you can click on any area of the scene now, and then you can see that this little dude will have calculated the lowest cost path using the navigation graph that's built into Unity and is able to navigate itself to the destination. So this is like using the nav mesh agent, nav mesh surface component, and then the nav mesh modifier. So those three components in Unity that you can add in order to do pathfinding using the built-in pathfinding. Everybody, I think we are reaching the end of our journey into autonomous agents and AI in Unity, and we're coming to the end of our class. Right, so it's time to wrap up, right? This has been an epic journey this semester. We started out with a little void, a cube that could basically seek a position in the scene, and we made a component, mono behavior, to do that. Then we refactored that mono behavior to separate all the behaviors into their own mono behaviors. And we learned how to do arrive, and we learned how to do flee, and we learned how to do pursue, and then we learned how to do offset pursue, and then we learned how to do lots of different wandering behaviors. We learned how to do one which is based on jittering. We did one which is based on Perlin noise. We did one which is based on harmonic motion. Then we did, what did we do after that? We did all of that. We did the, we learned how to basically make our void, you know, swim in formation or move in formation with other voids by using offset pursue. And then we leveled up. We basically did loads of things using this entity component system in Unity, and we were able to scale up our void simulation to tens of thousands of voids. And using ECS and the same algorithms, you can simulate like maybe 20,000, 25,000 autonomous agents. All not all doing their own thing. We did separation, cohesion, alignment behaviors, and we also made a few other cool examples using ECS. We did the game of life. We did the Cytrans spiral generator. We did the voxel terrain. We did one where we used a job to deform a mesh. And then we implemented voids using entity component system, and we learned 30 cool things about ECS and voids. And then the last thing we did on the course was we learned how to make our little voids calculate paths between different areas. So now we can do all kinds of like emergent things and build, you know, complex simulations with autonomous agents which can find paths and follow paths and avoid obstacles. The avoid obstacle thing as well. And that's kind of what we did this semester. I don't know, for me it has been like a really great crack teaching you guys every week and putting these examples together. It has been really my pleasure. And this is our last class, you guys. So hopefully I'll get to see you in the new campus in TU Dublin, Grange Gorman in September. And that's pretty much the end of Game Engines 2, everybody. Hope you enjoyed it. And that's it. Bye bye, everybody. Anybody else ask any questions or make any comments or anything before we go, or we'll finish this live stream and we'll finish Game Engines 2. Wish you guys every success in the exam and success in your CA. I'm totally looking forward to seeing all of your space battles, and that's going to be great fun. So yeah, that's it, you guys. Have a great summer. It's great news yesterday. You know, I was listening to the news, and it looks like everything's going to get opened up over the next 3 months. And even the Taoiseach mentioned, he mentioned students and universities and everything. So, like, you know, it's looking good anyway for September. The dog is called Lucy. All right, guys, enjoy the rest of your day, everybody, and hope to see you in person very soon. Yeah, bye-bye. Oh yeah, let's have one last look at Lucy before we go. Bye-bye. Say bye-bye, Lucy. Hello, everybody. Bye-bye.